0.091. And then does it say successes or something?
X.
Oh, cool. X is 2 in this case.
Oh, so you just put that in?
Yep.
Okay.
So on the old calculator, we have to put it in ourselves. On the newer one, it actually asks you the inputs, which is kind of nice. You don't have to remember the
Or you can just spam it and
inputs.
Okay, that's the result. Thank you.
Sweet. So the rest of us have to live with this. Is that all right? So if you want to do, the nice thing is you have to do several of these in a row. Remember when you hit second enter, it brings up the last thing you did. So if I now want to do 3, and check that the first thing I did on your handout, it says 0.1996. When we did that 3, the one that's in red on the handout. So let's double check that. There's 0.1996. Thank God. Okay, cool. So the calculator basically just does that formula. That's why they come out the same. So it shouldn't be any amazing. But it is a nice, concise way to get it in there. If you're having trouble with your choose and all that kind of stuff, you can check it here. All right. So I know at the end of class last time, we kind of quickly did the mean and the standard deviation. But those formulas are just so nice.
At least one.
Oh, yeah. So again, what's always true about
1 minus none.
Yeah, it's 1 minus none. As long as, when we're counting things, the probability of at least 1 does this is 1 minus the probability of none. And how do I set this up? This formula here. So how would I set up the probability x equals 0? How many people do I have? 44. I want to choose how many?
2.
None of them.
None of them.
Right, I'm doing the probability of none here, right? So how many successes do I want? None. How many failures do I want? 44. And again, some of you guys might realize this is 1, so you really just have to plug that in. So if you do 0.909 to the 44th power, what do you guys get?
But if I see the probability that the 2 has diabetes,
So 1 minus that,
1 minus 142. Why don't I subtract this one? Because this.
because that's the probability somebody has, that we have 2 with diabetes. So the opposite of that would be not 2. 0, 1, 3, 4, up to 44.
Yeah.
I want probably at least 1. What's the opposite of at least 1?
0.
None. So now we have to calculate the probability of none. We haven't done that yet. That's the probability of 2. I now need the probability of none.
Yeah.
How are we doing so far? I mean, the nice thing with this is a lot of what we learn carries over. These are still just probabilities. So the probability of at least 1, we already know how to handle that. That carries over. What's new is, of course, how to calculate probabilities, but the ideas are all the same. What about part C? How do you get the mean? Yeah, n is 44. P was the 0.991, and what do you guys get there? 4? Okay, gotcha. So essentially 4. Yeah, I'm with you. That 0.004% always scares me, but it's just an average. It could be whatever it wants to be. So about 4 people. So if I had a group of 44 randomly selected San Diegans, and by the way, this is true. It was accurate as to last semester. I haven't looked it up since then, but let's pretend like it's still the same. If I picked 44 San Diegans randomly, I would have the average number, the people I would expect, the number of people I would expect to have diabetes out of the group would be 4. Now the second part will tell me how much I expect that to deviate by on average. It's not always going to be 4, is it? Probability is never about absolutes. It just says, it's probably going to be 4. Give or take how much. Right? That's what this would help me get. So how do you get the standard deviation? Square root of 44. And some of you guys might be savvy enough to realize that you've already done.
And the cube.
Or you just put the whole thing in again, it's okay. It's okay if you don't see that. So if you do the square root 44 times 0.091 times 0.909. What do you get? Well, what did I do? I get 1.908. Yep. We stop right there. Let me make sure everybody's with me. You doing okay?
Can I put it for this one here?
Definitely. That
Yeah.
whole thing is here. So multiply that by that, and then take a square root. Good, good. So every time we learn a new way to give data, we first learned if you just give me a big list of data, then we have to do that. The mean is add them up, divide by n. The standard deviation was a huge table with the x minus x bar squared and all that kind of stuff, which was a lot of fun, right? Maybe not the last thing I said. Then I gave you, what if I give it to you as x and p of x? How do you do it? Okay, now you get the mean is the sum of x, p of x, the expected value. Standard deviation was sum of x squared, p of x minus b squared. We had formulas for that situation. Now we have a binomial distribution. It's a new situation of how to give somebody data in a specific situation, right? So now we have to have its formulas for finding the mean and the standard deviation. They mean the same thing as before. So how do I figure out if 9 is unusual? Of course, in red, I tell you how to do it, but we should know this already. If I do the mean, unusual is anything outside of 2 steps away. So if I take the mean and I go up 2 steps, where would I end up 2 of these? Yeah, like 7.8, 1.6, something like that. 2.4. Yeah, thank you. I forgot the 04. So we'll say 7.8, and then down 2 steps would be where? Yeah, 0.1 something or other, right? So is 9 unusual? Bless you. Would 9 people be unusual? Yes. And this gets to the point. Have you guys heard of now this is where you got to be careful with probabilities. Have you guys ever heard of like a cancer cluster? Where, you know, and sometimes it's true, they'll find areas where an abnormal number of people have cancer there. So they do exactly this. What's the expected value of number of people that are going to have cancer? And then I see, oh, there's way more than I thought there would be. Right? So if I went somewhere and I took randomly 44 people from a certain neighborhood, and I saw 20 of them had diabetes, I'd say, well, that's evidence that something freaky's going on here. They all must eat something that they should not probably be eating or something. Or some genetic thing is going on. You with me? Kind of with me? So with the cancer thing, very often they'll blame, we saw this happening. We saw little areas where more people had cancer than we thought, than we expected. Not every one of those is going to be there because something's causing that. Randomly, that's going to happen. If I pick 44 San Diegans, I could very well get 40 of them that have diabetes just because they didn't pick well enough or just because it's going to happen sometimes. But it's more evidence that it's more likely that something's going on other than I just happened to randomly pick that. Are you guys kind of with me? Yeah. This kind of sounds like stuff I've said before, and it is. It all comes back together. So in this case, if I saw 9, is that is unusual? Is that necessarily unusual enough maybe to make me go, whoa? Well, that's what we're going to get into later when we start really testing this. How truly unusual is that? At this point, you guys can just tell me that's unusual. Can you give me a feel for how unusual that is? Not really. You can say, well, it's not that far away from 7.8, but we haven't learned yet how to tell how unusual that is. And that's coming very soon. All right, how are we doing so far? Is this?
How did you get this 7.8?
2 steps up, 2 standard deviations up. So take 4.004 and add 2 of these. Same thing we've been doing, right? Now be careful. Why can I not say there's 95% in here? You guys see where I got that number from? Why can't I say there's 95% of the information in here?
We don't know.
This is 2 steps.
We don't know if the normal is.
Yeah, we don't know if it's normal. So don't bring that number in too often. It's only if you know it's normal. I don't know if this is normal or not. I have no idea.
But it would be 68%.
Yeah, exactly. If I saw that, it would be, well, 68 would be within 1. Within 2 is 95.
If it's normal. But
If it's normal.
What if it's not normal? What's the
Then we can't say.
Well,
Chevy Chef comes in and says it's got to be at least this much, but that's, not the most helpful.
What's the at least for 2?
75. So it's going to be at least 75% of San Diegans. At least 75%. Now this is where it gets a little weird with this problem. At least 75% of the time, if I picked groups of 44 people, at least 75% of the time, the number of diabetes cases I'd see would be in between these two. Anywhere from 0 cases up to about almost 8 cases. Maybe. I like that. So you guys are looking on. What the hell's going on? All right. So again, I'm always of two minds on this because the math very often is easy. I don't know if you guys agree with me, but the math is easy. The concepts are freaky. That I understand. That's why I keep trying to go over those concepts. Okay. So now what I want to do today, what I need to do right now is run back to my office and get another handout that we're about to step into chapter 6. And I don't think I've said this a couple times. Chapter 6 is probably the most important chapter in here. All right, it's sort of like the solve an equations chapter in algebra. If you don't know how to solve equations, you're screwed. So if you don't understand chapter 6, you're basically screwed for the rest of the semester. So I really want to go through and get into chapter 6 gently, I guess. So I'm hoping this handout will help us.
I didn't get one of the ones that you just passed out. I know you were down to your last one.
I'm not sure.
Oh, cool. All right. So let me run to my office. You guys talk amongst yourselves.
Yep. It was ridiculous.
Much better than last time.
It was ridiculous.
It was like, I felt uncomfortable at times, like watching them like in the hallway.
Yeah.
Like, being like,
They felt like they were human beings for once, though. Did you get that impression that they were actually real people, not just like random talking
I
points?
thought it was funny at times. Like I just felt, I don't want to get it. Like, I have very specific political views, but like, I was just like, there's just something that like pissed me off, like when I was watching that campaign.
Why, are you all for Obama?
No.
No?
No.
Oh, you're for Romney?
Yeah.
Oh, okay.
Why do you think I was for Obama?
Because you said something earlier to the teacher about the whole abortion
Yeah,
thing.
I'm like totally against that.
Oh, okay, good.
I was like wondering,
Yeah, no, just because like a lot of women are like, oh, they're trying to like,
That's why I
there's
know
a war
that.
on women and all this crap.
yeah.
No, I was telling that to my mom. And I was like, there's not a war on women. They just don't want to have to pay for people's birth control.
That's ridiculous. Forcing, he's like, I don't believe in the government forcing people to like put into their body. I'm like, you're forcing businesses to give women contraceptives.
Yeah.
That's actually how. And I just made me really mad. I'm like,
Yeah, it's like women are in control of their own bodies and stuff. Okay, well, what about the 500,000 women that are killed every year from abortions? Those would go to be women.
they're like, he just. The reason I knew that statistic was because I obviously look at both sides. And
Yeah.
I knew that a lot of women vote for him like that. I'm just like,
Yeah, there's a war on women.
I just don't like the law.
I actually don't like either one of them.
No, I just think I'm always like,
I thought the debate was interesting, but I'm not going to vote for either one of them. In California, did you
Let's keep
watch
this
the
civil.
debate?
Huh?
Did you watch the debate
I
last
haven't
night?
taped that.
I've done that for the past two
I know.
debates, and it's like you just feel
This is the
stupid because
first
everyone
year I
already
haven't
knows.
actually seen anything live. I'm like, come on.
All I can say is the last 3 debates have had like the worst moderators I've
I
seen.
know,
Like,
she was so biased.
they also suck at making the candidates stop talking.
I know, it's so sad. They just talk over them.
They're like, that's funny, I'm not done talking. This is supposed to follow the rules.
The first day was, well, there wasn't too much debate in the first.
Yeah. No, the vice presidential debate, they totally didn't follow the rules.
I didn't really watch that. I recorded it, and fast forward, you could just see Biden laughing through all the records.
I'm not sure how he could reply other than that. What's that? Will we? Yes. Move on.
You can give us your opinion.
In fact, a week from today, we're going to have a quiz on Chapter 5. So we just finished Chapter 5, so Chapter 5 homework is due a week from today, so that Wednesday. So don't blame him. Don't worry, I was going to say that anyway. Don't everybody,
Wait, can you say that again?
To make it official, Chapter 5 quiz a week from today, next Wednesday.
And that's a win the homework review.
And that's everything we've already done.
Yeah. Again, I say due with quotes because it's always due by the day of the test if you need more time. But I never try to put a quiz on a day until that homework is actually kind of due that day. Right?
Okay. Is that in the syllabus?
I don't know.
Did we get our homework back?
What's that?
Did we get our homework back?
Which homework? Yeah, there's a lot of homework I haven't given back because there's a lot of people turn it in on the day of the test. So, like I told you, that I'm going to do as I can, which I have not been able to do.
October 24th.
In general, I'm just happy, for example, that I graded that quiz by today. I was happy. So here's my attempt, and to bridge the gap from Chapter 5, which I don't know if everybody believes me in this, but Chapter 5 is really not that bad. It's really very precise. The formula is always the same. You can really sink your teeth into it. Chapter 4, to me, as a student, I would be a little more vague sometimes. Chapter 5 is very specific. So what I'm trying to do here is to get us into Chapter 6, using some of the stuff we know from Chapter 5 to help us out. The thing about probability distributions, so we have like binomial distributions. So let me show you something from the book before I get to the picture I have on this handout. Oh, let's see, it's page 603. I think. Yeah. So look, for example, at so this is the page 603 is the binomial probabilities table. So to kind of reference the table, there's a couple of homework problems that ask you to use this table. We're not going to really use it on a quiz or a test. I just want you to know it exists. The table is kind of lame. I gotta stop saying that because it's not bad. It's just that probability. What if I have a success rate of 0.372? Can I use this? No. If I could, this table would be stupid big. Your book would be this thick. So let's screw that. So this is kind of a nice visual, though. This is one reason why I think they put this in here. I can very quickly reference, for example, if I had 13 people and the probability of success was 1%, say the percentage of people that have been to Guatemala. So 1% of people have been to Guatemala. And I have 13 people. So you can see how to read this. 13 people, N is 13. The probability of success is 0.01. So all of these are related to my problem. So of course the most likely thing, if I have 13 people and there's only a 1% chance that anybody went, the most likely thing would be none of them went. You with me?
And 0 plus is
At least 1 or 0.
Because what's 1% of 13? What's the average in this case? What's NP, 1% of 13? Don't take your calculators out, make you cry. Just move the decimal back once, two, right?
Yeah.
So the average would be 0.13. That's basically 0, right? You with me? So if you look at that first list, what's the highest probability? 0, right? That's got a probability of about 88%. There's an 88% chance that none of them will have gone. So if I were to draw this first column here, so there's 13 people, there's all the possibilities, and here's all the probabilities associated with those. If I were to draw that, it would look like this. What would be the tallest bar? Yeah, it's 0. I got to pull 0 over here. That 0 would go up to like 0.88. And then it would go 0.115, 0.07. Good Lord, right? And then 0 plus means it's not really 0, but it's basically 0. So that's what it means in this chart. You with me? They didn't give enough room to really write all the decimals. All right, so far so good. Is that normal? Can somebody tell me why is it not, why did it not even have a chance to be normal? Where should the mean be if it's going to possibly be normal? Because to be normal, what has to happen? You have to go up to it and then down from it, right? So the mean for this really should be more in the middle. You don't want it to be too far down, and you don't want it to be too far up, because then you don't have a chance to go up and come back down. So the one on the handout is about 14 with a probability of success of 0.5. So you can imagine, if I have a probability of success of 0.5, that's going to be symmetric. Exactly half of 14. 7 is the average, so 7 is going to be right in the middle. So if I made the histogram out of it, so I didn't have to make a crappy one up on the board. So there's the histogram for that situation. So I just took the values from the table. For n equal 14, there's the values. Actually, there's the copy of the table. So there's the histogram. Does that look normal? Yeah. Yes, it looks very normal. And we're going to talk about, later we're going to talk about a test we can do to really see if it's normal or not. There's a certain specific number it's got to hit somewhere that tells me if it's normal. But just for right now, it definitely looks pretty damn normal to me. So here's the cool thing. And actually, let me come back up here for a second. Let's double check a couple of these things. Help me out. How would I do? Let's see. Blah, blah, blah. So if we flip a coin 14 times, what's n going to be? 14. What's p? Yeah, 50-50 for heads or tails. And q, of course, like I just said, 50-50. Cool. So the probability exactly 9 heads. How would I set up that formula? Good. 14 flips. Choose 9 of them to be heads. So how many of these do I want? 9. And how many of these do I want? 5. And of course, some of you will realize it's always going to be 0.5 to the 14th when it's a 50-50 chance. But to set it up by the book, that's the way it would look. How are we doing so far? We okay? And then what do you get when you actually plug that in the calculator? 12.21%. Okay. Bless you. Cool. So 0.1222 roughly, right? If I round it to 3 places, that's 0.122. Bless you. Right? Nothing major there. And if you look down here, we just kind of double check this. 9 successes would be a 12.2% chance. So that's where they get those numbers from. Nothing amazing. Yes, sir.
So that column is the 0.5 column?
Yeah, exactly. All right. And here I kind of step you through how to do the binomial PDF stuff again. So this whole thing's really on your calculator Bible. And here, what's the mean of this going to be? So if n is 14, p is 0.5. So half of 14 is 7. And this variance is going to be np times q. Yeah, exactly. Half of 7, really, 3.5. And the standard deviation is going to be the square root of that. Bless you. And what's the square root of 3.5? 1.871. Cool. I like it. How are we doing so far?
What's that number? 14 times 0.5 what?
Sorry. So N, P, Q. Sorry. Yeah. Oh, sure. Go ahead. You know where it is? How are we doing? We okay? So N, P, Q. Right, 14 flips, 50% chance success, 50% chance of failure. N, P, Q. So that's the variance because I haven't square rooted yet, right? And there's the square root of it, so there's the standard deviation.
And the mean?
The mean is 7. N times P. 14 times 0.5. So enjoy these formulas, especially compared to what we had to go through before, if you think back. Okay. Can somebody help me out with this? Minimum expected number of heads, the maximum number of heads.
0, and then that's
Isn't it the
7.
No, it would be
So we have a mean of 7. How far up do I go to find the max, and how far down do I go to find the min?
it would be 5 minimum and
So you have to add 2 of these, right? Exactly. So 2 of these is 3.742. I think, or something. 3.74. So this will be 10.74. You guys semi with me? Because what's unusual and what's usual? Within 2, with outside of 2, yeah. So I want to go 2 steps up. So if I take 2 of these steps, 1.87, 1.87, I end up at 10.74. If I take 2 steps down, I end up at, I forgot now.
3.26.
Thank you. How are we doing? Semi-decent? Okay. Now, I want to make this point to you. This looks pretty normal, right? This looks pretty normal. And we expect them to be between there. And since this is pretty normal, what percentage should be between here? If it is normal like we think. 95%. About, if it's around normal. Okay? So if I do look between, like here, and where does it go? Here. And I add up these probabilities. Does it come out to be about 95%? Let me take a step back. Let me make sure everybody's with me. We just figured out how far up and down to go to find the usual values. And that's because 95% of the data is in there. So if I look at the picture, is 95% of the data in there? It's not going to be exact. It's going to be pretty close. What's come out? 12, 36 roughly. Where am I at? 56, and then another 36 is like
I got 0.941.
941? That's pretty damn close. Okay. All right, so I just wanted to do a couple of quick little things that we've done before and see how they're the same thing on this picture. Now, here's the main part of this is going to help us get into chapter 6. What is the area of, for example, this rectangle? What's the area of that rectangle?
7.
No. How wide is it? 1.
Oh, it's
How long is it?
2.
0.209. So what's the area?
0.29.
0.209. So if I want to know the area from 0 up to 7, right? Maybe from 0 to 6, let's say. You with me? So at most 6. And I gave you a little bit of a at most, and at least, and all that kind of troubled people. But I was thinking about at most 6 people can be on this elevator, or else we're going to die. So I don't want to have 7 people in the elevator. I want to have 6 or less. How would I get the probability of at most 6? Add up all the areas. I love it. So there's a connection between area and probability. This is easy because there are a bunch of rectangles. That's kicks ass. The rectangle area is the easiest freaking area besides the square. You with me? The minute we start doing like normal distribution, can I make that rectangles? It's curved. That's not going to be a rectangle. That's going to be a funky, so if I have a normal distribution and I want to do the probability up to here, can I make little no, I make these little weird curved top deals. You with me? So is the area here easy to calculate? No, but the idea is the same. If I want to know the probability of this, I just have to find the area of this. Because the area is the probability when I draw it like this. And what's the whole area of this got to be? 1. So the whole area of any distribution when I draw it has to equal 1. We know that. Right? The thing that we didn't really know is the connection, the direct connection between area and probability. So thank God that when we do this problem, we don't have to draw a bunch of funky curvy rectangles and figure out the geometry. This is not geometry class, right? What you'd actually need here is calculus to do this. So thankfully we're not going to do calculus. we're going to stand on the shoulders of people that actually had a computer do calculus for them, and we end up with this table of probabilities. This is the z-score chart. So I'm going to use this here in a second. That's the connection between 5 and 6. 5 sets up histograms of probabilities for these binomial situations, and I see the area is the probability. So when I get to here, I don't want to know the probability between something and something. I just have to find the area in there. And that chart tells me the area. Thank God. So let me do a quick problem from chapter 6, which you're going to see in chapter 6. Actually, I'll do 2. I'll try to sneak 2 in here somehow. The first one is one that I want to do with you just to show you that, just to give you a little more trust in this chart. What do you know already within 2 standard deviations in a normal? How much is there? 95. So if I start at the mean and I go down 2, you can do it, Jeff, up 2 and down 2. There should be 95% in there, right? Okay. So somebody help me out. These numbers here, what are they really?
Standard deviation.
They're z-scores. I love it. They're numbers of standard deviations away, which is a z-score. These are z-scores. So if I could find the area between a z of -2 and a z of 2. You guys with me so far? Okay, and actually, let me make this a little bit easier for us in the early going here. How much stuff should be down here?
5, 2.5.
2.5, right? There's 95% in. There should be 5% out. 2.5% on that side. So it should be 2.5% or 0.025. You guys semi with me? So here we go. If you still have the insert in your book, this chart's on the insert, or it's in the very back of your book. Hopefully you didn't get hungry like I did at some point. Get your fiber. So if you look up, here's how this thing works. And this table takes a little getting used to. Do you see up here the chart is trying to tell you what it tells you? If I look up a z-score in this chart, what does it tell me?
The area.
What's that, the area where?
After the negative zone.
The area below it, right? So if I look up a z-score, it's going to tell me the area below that z-score, always. So if I want an area above that z-score, I have to do something with the number it gives me. The chart can only do so much. Thankfully here, what area do we want exactly? We want the area that is below -2. So if I look up z of -2, and if I wanted -2.02, I'll go -2.02. Do you see how to read this? That was a nice quick way for them to put, instead of having this long ass thing you have to roll out. They just kind of did it here and there. So that's always the second decimal place. So we want exactly -2, -2.00. And what is it? 0.0228, really close to 0.025.
Wait, so what are the other numbers up top for? Like, how do you know you use 0.0228?
Because I want, for this problem, I want the area below a z of -2. Right? That's what I want. Just to check it out with the empirical rule. And like I told you when I first did empirical rule, these numbers themselves are not exactly right, but they're close enough. Right? And now we're seeing that it's not exactly right. Not 0.025, it's actually 0.0228. But would you really hit somebody over the head for that? You're like, that's close enough, dude. Right? So that's the real exact number. But to make the empirical rule a little easier to remember, we made these numbers nice whole numbers. Where we could. Okay, maybe. Let's do one more and then I'll let you guys out. So let's say I wanted to find, and let me show you exactly how you should do this. This is maybe a little more than a suggestion, but it's not quite, you have to do this. If you don't do this, you're probably going to screw up. Let me say it like that. In fact, let's not even do that. You don't have to do that. So let's say I want to know the probability that z is more than 1.18. We currently can't do that. Because the empirical rule is only good for 1, 2, 3. It can only handle whole numbers. So here's my 0. Where's my 1.18? Over here somewhere. Now please, dear God, I get people that put numbers just anywhere they want. Draw the picture correctly. Right? This is a number line, so 1.18 is above 0, negative numbers below it. Trust me, people screw themselves up. And then shade in the area that you want. So you want a nice visual to confirm what you find. So what area do I want? Where do I shade? Yeah, above this. I want that area right there. So if you look up 1.18, and these are the negative z-scores. So let me go over to the positive ones. What do you get when you look up 1.18? 1.18. Now where's that on the picture? Where's 0.8810? Where's that area?
Above.
What's the sheets of chart always tell you? It always shows the area below. So you immediately put that number here.
Yeah.
Is that the number I want? No. So what must this side be?
-1.
Yeah, 1 minus this. Nothing new there, right? If I got that side, the other side's got to be 1 minus that. So what's 1 minus 0.881? 119, 11. So the probability that somebody had a z-score of more than 1.18 is going to be almost 12% chance. So next time we'll connect this with the real world, which is always nice. Right now this is all z crap, that's not real world yet.
So we need that chart.
Yes. I'll give you copies of the chart. That'll be helpful. But you should have it in the back of your book.
Can you find out P of at least?
I understand that.